Welcome back. So now that we know our double angle identities, we're going to use some double angle identities given some vague knowledge. So it doesn't seem like we have enough information here because this is kind of a conceptual problem, but we are given tangent of theta equals -3/4, and we don't know what theta is, but we do know that theta is in quadrant 2. So we're going to find the following three values: sine double angle, cosine double angle, and tangent double angle, or sine 2 theta, cosine 2 theta, and tangent 2 theta. Now, I'd like to point out that we know these double angle identities and we learned them in the previous video. So if you are unclear on these, you might want to pause, stop, skip back to the next video, and make sure you know what these double angle identities are, how we derive them, where they came from, how we use them. Anyhow, we know that sine 2 theta is 2 sine theta cosine theta. We actually know three double angle identities for cosine 2 theta, but I'm just going to write one: cosine squared theta minus sine squared theta. And then we know one for tangent, 2 tangent theta over 1 minus tangent squared theta. So we're going to find these three values, and then using the three values, we're going to determine the quadrant in which our double angle falls. So let's take what we know, and our first step, especially when we have something vague, is to draw a picture. You're right. That's what you said, right? And we're going to draw a reference triangle in quadrant 2. So I'm just going to draw a triangle coming up here. I'm going to drop a vertical down to the x-axis in order to make that reference triangle. Of course, we are talking about some theta value, which is a rotation off the positive x-axis, an angle in standard orientation. But the reference angle we're going to use down here, we're going to call that theta. Technically, we should use a different variable, but for the sake of not confusing you, I'm just going to leave that as theta. But we can't call this large obtuse angle theta and the acute angle theta. So really, it's kind of like alpha. But I'm going to take that out and just put this one little theta there so it doesn't look as confusing. Okay, so we know we are in quadrant 2, and we know we have tangent theta is -3/4. So let's think about our right triangle trig. Tangent is opposite over adjacent. So opposite is going to be 3, adjacent is 4. Of course, we have a negative value, so one of these needs to be negative. The 3 is going up, so that's a +3. The 4, we're traveling left on the x-axis, that's a -4. And then to find the hypotenuse or radius of this reference triangle, we just use the Pythagorean theorem. 3 squared, 9, plus 4 squared, 16, that's 25, equals the radius squared. So we have a 5 here. Now, our identities, you can see we need sine and cosine. So using my reference triangle, I can write that sine of theta, sine is opposite over hypotenuse or radius, so 3/5. And cosine theta is adjacent over hypotenuse or radius, -4/5. And I'm going to go ahead and pull tangent theta down here because when I scroll up, we won't see it. So tangent theta, which was given, is -3/4. So now if we want to find sine of 2 theta, well, that's equal to 2 times sine theta, 3/5, times cosine theta, -4/5. Simplifying, I've got -24 over 25. That is my sine double angle value. So cosine 2 theta, that's cosine squared. So we've got negative 4/5 squared minus sine squared, which is 3/5 squared. Here I have 16 over 25 minus 9 over 25, and 16 take away 9. This is going to give me 7 over 25. Lastly, I have tangent of 2 theta. Now, that is 2 times tangent theta, negative 3/4, divided by 1 minus that tangent theta squared, so negative 3/4 squared. So that would give me in the numerator negative 3/2, and in the denominator I have 1 minus 9/16. 1 in 16ths, that's 16 over 16, and 16 take away 9, that's going to give me 7 over 16. So I've got negative 3/2 over positive 7 over 16. And copy, change, flip, that's negative 3/2 times 16 over 7. Which is negative 48 over 14, which reduces to negative 24 over 7. So the tangent double angle was considerably more work than the other two to calculate. I want to ask you, do we know a ratio that is equal to tangent? So thinking about your identities, we know that tangent is equal to sine over cosine. So tangent 2 theta is going to equal sine 2 theta over cosine 2 theta. So I could have shortened this calculation by saying, well, this is sine, I found that above, negative 24 over 25, divided by cosine 2 theta, 7 over 25, and that again simplifies to negative 24 over 7. So we had kind of a shortcut method for us to find this. So we found 3 double angle values, and we want to know for the last part of this problem, where does 2 theta lie? So we have a sine, a cosine, and a tangent value. Now, we knew it was in quadrant 2, and maybe the smallest reasonable angle in quadrant 2 might be 91. If we double 91, that would take us down here to 182, and 182 is in quadrant 3. And you might say, well, Ms. Stein, I know it's going to end up in quadrant 3. Well, is it though? Because if I had an angle right here, that would be in quadrant 2, 179, and if I double that, I would end up over here in quadrant 4, 358. So which quadrant am I in? Am I in quadrant 3 or in quadrant 4? Well, we found a sine value. My sine value was negative. My cosine value was positive. And my tangent value was negative. So in which quadrant is cosine and secant positive? And that would be in quadrant 4. So I hope that helps you just, know how to use your double angle identities inside a calculation. I like this problem because it is conceptual and you have to pull together lots of knowledge in order to solve this. All right, hang tight. We're going to do some more examples in the following video. We're going to talk about half angle identities coming up.